Six Sigma Greenbelt. This is the fourth week of the first class. And this is where it starts getting tough. Statistics has always been a struggle. And I'll tell you right up front, if you have problems, let me know. I think part of what you need on a STEM course, any STEM course, is to see it being done. So what I've done is if you have problems, you ask a question in the discussion. I'll get to a whiteboard and I'll actually work out the answers. You can see it live. Again, let me know, okay? Now go to the whiteboard, post a link to a video, and you can watch me do it, okay? There's a couple different types of statistics. There's descriptive statistics. This is numerical. They basically describe measures. And if it's statistics, it's calculated from a sample. And a sample being, well, random sample, is that every member of a population has an equal chance of being picked and studied. A population is the entire thing that you want to look at. So when it's calculated from the population, that's a parameter. There are two most important things. You want to know where the center is and how much it varies. And the center point we're going to do by the mean or the average, and how much it varies is going to be using the standard deviation. Again, the population is everything we're studying, every possible observation. A sample is randomly selected from that population. And by definition, a random sample is a set of items that have been drawn from a population in such a way that each time an item was selected, every item in the population had an equal opportunity to appear in the sample. So everyone has a chance, and the odds don't change as you pull the sample. Now that's all good, and descriptive statistics are good, but what we wanted to do is inferential studies. In other words, we draw a conclusion about a population based on what we find in the sample. Deming, who's like the guru of quality, said an action taken to improve the performance of the future. Enumerative studies, Deming calls actions that will be taken on the universe. In other words, inferential studies is going to tell us something about the future. We can predict what's going to happen in our process, product, or whatever it is we're looking at. Descriptive statistics tells you it's a snapshot of the way it is now. If you have a computer-based program like Excel or OpenCalc, or you can get free calculators on the line, or there's some like Minitab, you can find the average. Just basically you put in your data, you type equals average in the case of Excel, left parentheses, highlight the data, right parentheses, and it'll tell you the average. Standard deviation is a little bit more tough. This is an example here. If bars have 5 gold pieces and they got the weights there, we calculate the average. And we calculate how far each one of those points is from the average. So in this case, the average is 5. So we take 4 minus 5, 2 minus 5, 5 minus 5, 8 minus 5, 6 minus 5. We add up those differences, and then we square it to get rid of the negative sign. Add up those differences. Then we calculate the standard deviation, which is equal to the square root of that 20 divided by my sample size, which is 5. So it's 20 divided by 5 equals 4. The square root of that is 2. And this is roughly, if I were to pull something out at random, these 5 gold pieces, the average distance that gold piece that I pull out will vary from the average of the total is 2. So I won't find many 5s, but I'll find a whole bunch between 3 and 7. A couple different formulas for calculating standard deviation. The sigma, which is the population, you know, if we're talking about population, you're going to use Greek letters. We just basically take each individual site, minus it from the average of the population, square it, divide it by the total number, right? Notice the capital letter on the total number of the population, and then take the square root of that. If I'm talking about a sample, there's a little fudge factor in the same thing, except I take n minus 1. We're going to talk about that later on when Gossett did the student T. But a sample, we do the n minus 1 population. You use the entire population number. Hopefully this looks a little bit familiar. This is a normal curve, and what Gauss did is he found that generally all things that vary randomly, that if we take that standard deviation, about 68.26% would be within plus or minus 1 standard deviation of the mean. Or if you take out 2 standard deviations, you have about 95%. You go out 3, you darn near have everything. Now that's important. Think about this. I'll use the example. You go to Walmart and buy an apple. You look at all the apples. There's some average weight of an apple. You're going to have a tough time finding that average one that's exactly, let's say, 4 ounces. But let's say the standard deviation is 1. You can find 90s, or about 68% of everything will be 3 to 5 ounces. And if you go out 2 standard deviations, 95% will be between 2 to 6 ounces. And almost 100% will be between 1 and 8 ounces. All right, let's talk a little bit about probability. Probability is a percent of all things possible. So if I were to roll a dice, the chance of me getting a 1 or a 2 or a 3 or a 4 or a 5 or a 6, it's got to be one of those. 100% chance I'll get one of those numbers. However, the chance of me getting a 2 would be 1/6 of that, because it's 1 out of 6 chances. This is not a normal distribution. It's a uniform distribution. But it starts to talk a little bit about probability. Okay, the average roll on a dice is 3.5, and you can see how we calculated that. Now again, I said it's a uniform distribution, but what if instead of plotting just that individual roll, I rolled the dice 5 times, added those numbers, and plotted those on the curve? What would it look like? What would that look like? Before we do that, I'm going to talk about the central limit theorem, and we'll see if it makes sense. No matter what the parent population looks like, if it's uniform, it's a triangle, if it's normal, if it's fat, skinny, bimodal, or whatever it is, you can use the central limit theorem. So what I'm going to do, instead of just doing the individuals, I'm going to pull 5 out and take the average of that and plot the averages. And this is what the central limit theorem does for us. Instead of just having a funny shaped distribution, what the central limit theorem will do, will make it into a normal curve for us. And the larger the sample size, the more it approximates the parent population. Again, the larger the sample size, the more it will mimic the population that it came from. Again, as long as you have random variation and you take a random sample, no matter what that is, that sample, if you take the average and plot it, it will make a normal curve, regardless of the shape of the parent population. It's tough to analyze populations that aren't normally distributed. So what the central limit theorem does, it gives us an opportunity, or the ability, to analyze the data. Now, we talked about that dice. I'm going to leave that as a homework. If you can, roll the dice 5 times and plot the thing on I want you to go to asq.org and plot that and see what kind of curve you get. Okay? Again, roll the dice 5 times, add up the total number, and plot it using the histogram function on asq.org. 2 things. It'll show you what a central limit theorem will do for us, and it'll also get you used to using asq.org and the tools there.